we're going to talk about relative abundance data and what this actually means. So when we put the mass on periodic tables, what we're really telling you is that this is an average. It's an average of all of the elements found, and it's the average based on the percentage that they're found too, because we want to know which is the most prevalent. So we can't just add together, say if I have carbon 12, 13, and 14, I can't just average those together because carbon 12 is found a lot more than the other two. So it's almost like I have to do 12, 12, 12, 12, 12, 12, 12, 12, 12, 98 or so times. Carbon 13 gets one averaged in, and carbon 14 barely gets anything at all because it's found 1 times 10 to the negative 10th. So we have to take all of this into consideration. Now, when we find this, we call it relative atomic mass, but really what we're saying again is just that it's all the different types of isotopes. Now, we can think about this almost like how our GPA is calculated. So our GPA is actually calculated by the course hours for that course itself, times its total credit hours, times the grade you got. And we do that for every course, and that's what your GPA gets to. So that's how we find your GPA. Now, for atoms, so when we're looking at this relative mass, or the mass that we find on periodic tables, AMUs, so what we do is we take the percent found, we turn it into a decimal point. So I'm just saying divide by 100, because to turn a percentage into a decimal point, we just divide by 100. Multiply it by that isotope's mass, and then I keep doing that for all of the isotopes, the masses that they have, and the percentage that they're found. So I think it would be best to just kind of run through a couple of these problems, because once you see it, it's really not bad. It's just a thought process on it. So this is for lead. So lead has 4 naturally occurring isotopes found in multiple samples. Use the data below to calculate the atomic mass. So I got all of this data, but what does it actually mean? Well, the one I said a second ago is if we turn all of these into decimal points, multiply it by this column, add all these things together, that should give us the right amount. So if I do, I'm going to just start by doing the point, and I'm just moving those decimal points over. So I'm just going to do this, right? So in this case, I have 0, 1, 4, and that is going to be times 203.973. And I'm going to add it to the next one. So I'm going to move this decimal point over 2 times. I have 0.241 times 205.974 plus, move this over 2 times, we get 0.221 times 206.976, and then we have one more, which is 0.524 times 207.977. So we're gonna do all of this out in kind of one string, and that should equal the percent found, or the AMUs for lead. So all I'm going to do, because this is a scientific calculator, it's going to arrange this for me using the PEMDAS rules. But so I'm going to do the 0.014 times 203.973, and I'm going to add, I'm going to go 0.241 times 205.974 plus 0.221 times 206.976 plus 0.524 times 207.977. This is going to give me an equal of 207.1. So we get 207.01, and that's AMUs. And to just kind of see if you're right or right around where you should be, you're going to find that it's probably closest to your highest percentage found. But look at all of these ones found that were pretty over there too. So it's going to skew that number down just a little bit. But the number is going to be 207.01. So we can even estimate this slightly. And then my other question here is, which is the most stable? So when we think about this, what data do we find? Well, I took a sample of lead out in the wild, and I came back and I analyzed it, and I found these 4 isotopes, but I found this isotope more often than the other ones. So the most stable one is going to be the one that I find the most. So that is the PB or lead 208. Okay. Let's try this one more time, and I think we'll be pretty good at that point. So silicon, on the other hand, that has 3 naturally occurring isotopes. So we have silicon 28, 29, and 30. Now, just to get a mental idea, I think it's going to be closer to that 92, because like whatever one this is. So this is 27.977. So I think my final number is going to be the closer to this. Okay. So which is the most stable? I can already answer. It's Si 28, because it's found the most. It's found 92 times more than all of the others. So let's turn all of these into decimal points. And again, I'm just doing it the nice quick way of just moving the decimal point over. So we got 0.9223 times 27.977, and we're going to plus 0.0468 times 28.976 plus we have 0.0309 times 29.974. So we do all this math and we're going to add them all together. So let's see what we got. We got 0.9223 times 27.977 plus 0.0468 times 28.976 plus 0.0309 times 29.974, and it equals, and yeah, it's the closest to it, so it's 28.09 AMUs. So yeah, it's pretty close to that number, right? It's not as far off as 29 or even closer to 30, but it's still roughly around that number. So I think that we're in the ballpark. So 28.09 AMUs, and silicon 28 is the most stable. And you can also find out too which one's the least stable, because it'll be the one that's least found, or in some cases you won't find any of them naturally because they're so unstable. But if I were to find a natural sample and find a small amount, the least stable naturally occurring isotope of silicon would be this one. Okay, so with that, we have found our average atomic mass. We found where this mass comes from on our periodic table. And we found that we can pull this data from percentage found by its mass, and we can put that number confidently onto the periodic table. We can also use this data to identify an element. If I pull a sample and then I put it into this blender and find all of these different isotopes and masses, and I find them by the percent abundance, I put all this data together, it will give me the mass, and then I can go back to my periodic table and say it's this mass. So that's how we use it. That's why this is great for identifying minerals and other items out in the wild. So if I find a sample of this metal out somewhere and I find out that it has this particular mass, oh, it's zinc, the masses match. Or at least they're close enough for me to say confidently that it is zinc. So that's how we use it. That's what we use it for. So take this with you, and if you need help, I'm here always.